Yes, I am going to talk about 7 steps to build your data pipeline. I figured out, yeah, sorry for the confusion. I reduced the number of steps just so that it fits in the timeline and it's easier to grasp. And primarily, the way I've structured the talk is going to talk through some of our experiences and kind of our war stories. How did we end up doing it? And then before that, like, okay, I'll just explain who we are exactly. So, so who we are? We are a mobile game development company based out of Bangalore. We are Moonfrog. We are making mass market mobile games primarily for all Indians and Indian subcontinent. We are approximately 5 million plus daily active users as of now. So large scale in terms of product, and 15 million plus weekly active users. We make real-time cross-platform games for Indian subcontinent. We have been doing it since late 2013. So this is like pre-geo, post-geo. So we know this market for real time and all that stuff. Also, we are highly optimized for India and Indian subcontinent in terms of our product. The most important point is like, okay, we are a profitable company as well. What does it mean for data? Like, okay, what does it mean? Like, okay, we make mobile games, consumer products for this kind of scale. What does it mean on data side? Is our current ingestion scale is 20 billion unique events per day, and total size of data that we are ingesting uncompressed is 800 GB plus. No. Now, obviously, this is not the scale we had on day one, and this is not what we designed our initial or V1 of data pipeline to handle. But I'll talk through some of our learning, some of the journey, some of the decisions we end up making, and why. And hopefully, obviously, like all of you will not have the same set of problems or exactly the same things that we had to face or we ended up doing. But I hope that okay, some of the learnings or some of these things will help you make the right decisions whenever you are at the decision fourth point. Now, what we wanted on day one. So I've made sure that like I've added the for day one of your startup or day one of your product, because me like and my team like we were in game development for quite some time even before doing Moonfrog. So we kind of knew that okay how important data is, and most of the people here in this room for sure know this. Like when you're launching your new product, you want to know how users are using it, what's happening in the product, is it behaving the way you designed it to be, so all that stuff. So it's very important, it was very important to us that okay we kind of are very clear what we want on day one, not on day 13, not on day 365, or what on day one is absolutely important for product or business success. So these are some of the points. First, we needed access to data uh, of the product or the game launched immediately, like as soon as possible. Like when we launch a game, and I'm pretty sure for all you guys also who launch consumer product, when you put out the product on Google Play Store or website or wherever, you get one user in the first minute or first second or whatever. You get 100 users in the first day or something like that, or 1,000 maybe. You don't get a million users on day one necessarily, right? So you need to actually needed to have ability to kind of query row level at user level as well. Like okay, kind of know what did this user do, what did he or she ended up doing, clicking, where did they drop off, why, and all that stuff as real time as possible. Because we were making consumer products, games, we had to kind of do something like okay go in hands of the user, kind of see how this user is playing it, okay what happened, okay the loading time was too much or whatever, all that stuff, so as real time as possible so that we can fix it also as quickly. Second, cost sensitive. Being a startup, obviously we were a bootstrap startup, so we didn't have all the money, we had to worry about this. Infrastructure side, wanted to start with free credits as most of the entrepreneurs want to. Ops light, because ops heavy stuff will cause you too much pain in the early days and kind of distract you from building the actual thing, which is the product. Then resource. Also, like okay, for all entrepreneurs here, like okay, you do not have engineers just sitting around to do like okay, build your data pipeline all the time. So we realized that okay, we actually will spare half a engineer, like okay, half the resource, try to build something that we want, which we require in the early days, and then slowly as the product scales, then we'll scale this team to maybe one engineer, which is 100% growth, right? And then the last step also, we were very clear that okay, games, the kind of products we do, they have large scale up requirements. They do not give you time that okay, oh, hold on, do not play our games, we are currently upgrading our infrastructure, sorry, like users will move on. So we knew that okay, we need to have scale up capability from day one. But obviously, like, okay, you cannot scale up to whatever 100 billion or 100 million users or just like that. You don't want to over architect on day one. So we figured out a ceiling. We said shouldn't cause headache till 1 million daily active users. All right. So here are the 7 steps. I'll just quickly read through them, but we'll go into detail. First is understand your requirements and constraints, your business requirements and your operations, tech, and all those constraints. Second, think generic. I'll explain why it was super important to us, and hopefully there will be learnings here because we make mobile games. We don't make one mobile game. We have to make games continuously at some frequency. So we don't want to do data pipeline again and again. We don't want to figure out new data nomenclature and whole topology again and again. So we had to figure out or think something generic on day one. Third, produce data well. In games, like, okay, that data is the most important thing because you can't go to the user and ask him or her that, okay, oh, why did you stop playing our game? Or why did you start playing this game? Why did you like this or why did you not like this? The answer you're going to get is, oh, I stopped having fun or I had fun. And which is more or less not much useful to product developers like us. Fourth, design V1 of your data pipeline. Know that it will change and it's only V1. Fifth, open up, enable many data interfaces, primarily use the data. Make sure your company, your people, everyone is using the data as much as possible. Otherwise, no matter how much you ingest, if it's just sitting around, it's just a waste of resources anyway. Then tune and repeat. And last step, upgrade to V2. So I'll go through these 7 steps, our journey primarily, and explain Layoke in our context. So first step is understand requirements and constraint. We figured out there are 3 different verticals that we had to worry about. First is business, obviously. So what are business requirements and constraints on day one? Like they wanted real-time ingestion. They needed real-time ingestion so that they can query it as quickly as possible. Fast query speeds. Don't want to like I want to have this. I have this question in my mind right now that okay, why did this user stop playing yesterday? If I cannot get the result as quickly as possible, then other things will get important and it will just slow down my iteration speed anyway. Third, SQL query interface. This was a constraint that we put, a requirement that we figured out that okay, all our people, and we knew that okay, whoever we are hiring, SQL is the right interface to build on. Then row level granularity. As I said, we needed user level granularity. We can look at some aggregate stuff. Okay, how many people from Maharashtra played yesterday and did this? But then at the end of it, you'd actually need to get down to that one user, that one section, look at what happened, how the funnel actually looked like. Then rich events. Rich events means that okay, primarily we wanted all as much data as possible available in that particular row itself somehow, because SQL was the most important thing. We wanted every person in the company to write SQL, or more or less like that. Like okay, every product manager coming from anywhere has to write SQL. Data scientists, developers, maybe even QA. So obviously, like they are not gonna write 6 level of inner joins and all that all the time. Some people will do, but still, you wanted data available in the first level itself. Tech side, we wanted generic data design. We knew that okay, we'll make more products, more games, so we wanted data design to be generic. Forward and backward compatibility, very important because we are upgrading our products continuously. Product is not going to look like how it looked on day one after a month itself. So you want full compatibility, simple architecture so that it's easier to manage and all that stuff. Too much complication and all that will be a kind of a distraction from the actual products itself. Fourth was very important. That's a constraint we put: immutable data. We said these are all data events, analytics events. So data will be immutable. And that's upfront. Let's just talk about it. It has to be immutable. No, nobody is allowed to change it. You make a typo, fix it in the product, and it will start showing up better tomorrow. Ops, hosted services as much as possible so that we don't have to worry about ops. Scale out capability. And resilience to bad queries. This is also very important. We knew that, okay, everyone in the company, we want them to use SQL to kind of query themselves. So there will be bad queries. Someone will forget to put a limit, and it's all right. We have to have infrastructure which can handle to some extent. Now at bottom, I've given an example like, okay, what kind of queries we were talking about on day one, just to give you a flavor of what it. So how many users who played at least one game yesterday saw the bonus pop up for the first time? Now this is a very simple question in our business. This is not a complicated question which will come. And this itself, if you convert into a SQL, you will see that, okay, it will require a couple of inner joins to some tables, depending on what you do. And then the actual analysis starts. Once you get the answer to this, then immediately the PM or the data person is going to ask, how does that compare to last week or yesterday or something like that, or maybe last year sometimes. So all that is very valid problem statement for us. Let's come to the interesting part, which is the data schema design. Now we kind of listed down some rules like, okay, that we'll follow, where it has to be generic. We knew that, okay, we will add more columns later. Whatever we are going to capture today is not going to be sufficient. Tomorrow we'll figure out new columns or new angles to capture. So we'll add more columns tomorrow. And then normalization, like, okay, that's a debate in the beginning to have when data schema is being designed, how much to denormalize, how much not to. So what is right for us also. So this is a sample or like a subset of the tables that we ended up making on day one, like table count, table economy, and user. So just a quick explanation of what they are. I'll go deeper into one table just to give you taste. Is all generic event comes into the first table. Economy is our game currency, the virtual currency that is moving around. So inflow and outflow of that we manage in a separate table. User, and it's self-explanatory. Table open for some generic funnel events, and payment is obviously also self-explanatory. Now, how this helps is like this: like, okay, questions will be like how many users opened bonus pop-up. So we can just do a join of count and users. So simple joins can also tell you this data. How many users from Rajasthan played poker and rummy both yesterday? So this is a valid question for us to ask, or for any developer to even ask, or QA to ask on a daily basis. So you can do it with a very simple SQL query. Then how many unique users on iOS faced transaction failures yesterday? This also okay, is a very standard day-to-day operations query, right? Now going into one table in particular, this is the kind of like sample schema, um, how it looked on day one or as close to that. So there is something very interesting here. I'll kind of highlight that part. Is primarily this part where kingdom, phylum, class, family, genus. People will remember it from their 12th or 10th classes. Like, okay, this is something which we figured out or which we had experience with. That this gave us the right generic framework to build our data schema for across all games. Here, as you can see, nowhere it actually mentions anything about like how many, which funnel step exactly it is. Okay, which screen are we talking about? It is the loading screen, or it is this particular lobby screen, or checkout page, or not. Like, it doesn't talk about all this. The only identifier is game ID, which identifies different games, but that's it. Everything else remains very generic, and how we end up using it is something like this. So like start session is a counter or an event. We call it counter, but for it's a event that then you look at player load is the kingdom started, where it started loading screen. Okay, how did it start? Button 120 that the user clicked. Genus we leave empty. The rest is something there. And again, the user actually player load finished. So the same event is fired again, just with one item different, which is phylum being different. Now, just by querying on this table, actually I can do a analysis of how many people are dropping off, how many people started player load but did not ended up. And similarly for everything. So this one table itself, if you have access to no other tables, actually the product manager can be doing some analysis of figuring out, okay, how users are dropping off. Every single event, the whole session can be potentially replayed by just looking at that. So this was the second step. Third step coming to that is produce data well. From experience, what I've realized that, okay, we end up focusing too much on the infrastructure, too much on the usage, but forget that, okay, we have to produce data well as well. If you insert noise, down the stream, it's all going to be noise. And you're going to be spending time, money, and energy just removing the noise. So it's very important. What the rules that we ended up following is keep them dumb, Keep your data producer as dumb as possible, because your data production or data producers will lie inside the applications one way or other. And applications are going through a different cadence, like development cycles and all that. You're going to change it every single day potentially. So keeping this dumb is very important. Otherwise, backward compatibility will be a kind of a problem. Less transformations. We figured out that we don't want to do any transformations as possible. What you insert is what you is gonna get at the end of it, so that there's no logic being built on the data production side. Enrich the data, put as much contextual information at the point of data production itself. And misuse is okay. People will put in typos, people will put in test the limits, will make manual human mistakes, and that's completely all right. Data pipeline should not break due to this. So identify all data producers early on. And for us, it was just to give an example, the Android, iOS, or the web app, different apps. And we realized that what are the constraints there? We cannot keep sending each event or each analytics data over the network, because we are making real time games. So you want all the network to be available for the actual real time game as much as possible, not necessarily only for the analytics events. Then cannot lose data even if the app is crashing continuously or is killed or all that real world problems. Then keep out of context from the application itself, so that the application which is going through a different release cycle doesn't end up breaking your production flow. And simple solutions like batching to fix the um, network calls, and then local disk storage develop as an independent library. These are standard solutions we ended up applying. Similarly, huge server-side deployment as well for application, lots of microservices. So over there also we are generating lots of data, and not just for product, but also for tech and engineering and everyone else. Like all this is analytics to be used by different teams in the organization. So we needed to develop or send data from all our microservices, like without any differences, without any like, okay, segregation. So cannot keep sending each event over network and keep data collection agnostic of the microservice itself. These were again the constraints and problems that we had to do. So yeah, so what we ended up doing is develop basic but standardized libraries, lots of abstraction, simple functions where everything is just straight up in the function definition itself, and how you end up using is just count. And the similar, like you can see the kingdom phylum itself, which is as per the schema. So what you saw in the schema is exactly how it's getting produced as well. So actually the user of the library or the this particular SDK and all that stuff, they kind of know that okay, they also talk in the nomenclature of kingdom phylum stuff. So the application team and the data team is not fighting on the fact that okay, oh, I added something in the column 3, but I don't see it in the um, end table or the warehouse or wherever. That's not how we are talking. We are talking like, okay, I add, what did you send in kingdom? Do you see it in the kingdom? Okay, like you sent something wrong in the kingdom, it's your fault, not the data pipeline's fault. So that it remains very simple and agnostic of the games themselves. Now you come to the design V1 of data pipeline. Now this is a very typical data pipeline architecture: data sources, integration ETL, then to data lake, to warehouse, to all your reporting and BI. What we realized is we need to tweak a little bit. And the principles that we have followed is less number of layers, because you don't have unlimited time in the beginning. Keep it transparent. What you get is what you insert, and it's only V1. So we'll change it, and that's completely all right. So we knew, and this is the pipeline we started with. That data sources and data ingestion we kind of merged. We made a thick client which we called Squirrel, which is internally developed. It was a thicker client, and because we didn't have time to architect it fully, and directly inserting to data warehouse. This was the big, the like anti pattern, as we figured out, people call it in AWS. Like we ended up putting it in data warehouse and then kind of backing it up in data lake, and also doing archival in data lake for backup purposes separately, and letting users kind of query and dashboards and reporting and BI tools to directly query data warehouse as well, and some part of data lake in the beginning. Later we increased the interfaces, but in the beginning all the queries were happening on data warehouse. Now data warehouse you see is we use Redshift, data lake is S3, and Redshift we figured out, like I'll talk through why exactly and how it worked for us in the beginning. Now To explain the pieces in the previous slide, Squirrel was the data collector, which is a thick client written in Golang, deployed homogeneously, and processes event only once locally. Input interface was a local file which was being written by all the SDKs and all that stuff, and output directly to Redshift or S3, which is our warehouse and the data lake warehouse. So we started with DC to large. Anyone like familiar with Redshift knows this is the smallest instance that you can start with. Different user queues for ingestion and usage. So because we are live ingesting data as well as directly consuming it continuously in the beginning, and keep moving window of data. Now that's the most important part. Like, okay, Redshift, you cannot store indefinite amount of data. If you do, you can. Like they will like you, but you will end up paying huge amount of money to them. So we kept a small window, 120 days of moving window, so that the older data we are purging, you don't need it continuously. You can aggregate them and then keep it in a much smaller this thing, footprint. Daily unloads vacuum to reclaim space. S3 directly store in the format which works with the warehouse. So that is really helpful. So we stored in CSV so that we can directly do a copy command to Redshift to load it whenever we want. Now you have collected all the data, you have produced the data really well, but open up interfaces inside your company. You will be stuck there. If there is only one interface to kind of query all the data that you collected, somewhere you will face a problem. Someone in the team is not going to use the data to its full power. So we figured out we wanted many data interfaces. And again, the rule being keep it simple, transparent taxonomy, your misuse is okay, and use third-party interfaces. So direct SQL Workbench evaluated several tools, Metabase, Redash, and standard Python scripts to business reports. Uh, we realized some problems early on, realized temporary need for extra data in some tables sometimes. Because we had a moving window, sometimes people need the last month's data also or last year's data. So we created Rundeck automated jobs which users can run to do on-demand tables. And also sometimes more historical data is needed. Like, okay, last year IPL, what was happening? So that kind of stuff we figured out much later, and we created ad hoc Redshift clusters. So you kind of the clusters, you create a smaller set and do your independent analysis. And all these tools we ended up building so that our teams do not need data pipeline or data platform people continuously. They can just keep doing it themselves. Then tune and repeat. Not all data is important. Always backup, drop and rebuild very quickly, and data will continue to increase. So problems, bottlenecks in ingestion. We had to figure out solutions. So insert versus copy. We figured out that okay, copy, how to tune it properly, how many queues to use, what are the right variables to continuously like tune for our usage, our ingestion speeds. It will be different for different people. Parallelization requirement for ingestion solved by tuning the queues, and thick client, the also leading to CPU spikes. So optimization in file handling and Redshift and upload tuning also we had to figure out. So we ended up, for example, breaking the bigger tables into smaller tables as well, just to kind of give, these are just views to kind of give users a kind of easier access. Now upgrade to the V2. So this is what the data pipeline approximately looks like in our application now. Is all the different kind of producers here, different SDKs, different like in the client itself or in different microservices of different languages and different types. It comes to what we call, we upgraded Squirrel to Badger that we call, which is a whole pipeline which actually processes the data in different stages. I'll just talk about how this is built. And this is completely in-house. And then data is still directly going to data warehouse as well as to data lake. Both are still Redshift and S3. Also, we have added a parallel pipeline for smaller set for different product alerts, business alerts, and real-time dashboarding and all that stuff, which goes to memSQL. And all those warehouse and your real-time data store and as well as the data lake, all are directly accessible to our dashboard reporting BI and users themselves by doing direct SQL queries. Now, just explanation, Badger is a file ingestion client, which is thin file ingestion client written in Golang, rotates, moves files of NSQ. Then this was the Badger pipeline, which is a high throughput ingestion backend. We use all the pieces are written in Golang. We use NSQ for as like okay, kind of high throughput message passing, and archive files to S3 in CSV and Parquet format as well now, and batched upload to Redshift as per priority queues. and memsql for maintenance, like that's very standard. So this is our current scale. As you can see, games, we have a daily pattern. So like we, it follows the traffic patterns of the products as well. Total events per day is 20 billion plus. Total size of data per day is 800 GB plus uncompressed. Average events per second is 200,000 plus. Peak events, as you can see, goes till 350K approximately. And rows maintained hot, including aggregate tables, is 250 billion plus. Rest is obviously all backed up in data lake. We can load it whenever we want in ad hoc tables or in the main cluster as well. So this is what I had, a high level walkthrough of what our journey has been. Again, just to reiterate, these were the 7 steps kind of we ended up following. And thanks for coming and listening. Hopefully, if you have any questions, I'll be around. I can take maybe a couple of questions now, but outside, feel free to catch me and happy to answer any questions. Awesome.
We have 5 minutes for questions. So if a few questions.
Hi,
Yeah,
this is excellent presentation. Thank you.
thank you.
So the pipeline technologies look great. It's simple, easy to understand, but just want to figure out, what are the provisions for monitoring the data quality or any kind of data leaks happening.
Yeah.
So what are the metrics you use for monitoring the data flow or any miss?
So primarily, good question. Like we monitor, as we don't have, like there is no differentiation between data for the pipeline. So what we just are looking at in different phases of the pipeline, how many rows we are processing, and we look at that itself is also getting ingested in the pipeline, and we look at that live. That okay, are we, how many rows we are discarding due to bad formatting or something of that sort, and how many actually we are able to parse through the funnel. And if that crosses a threshold, then that's an alarm, but generally never happens because we are not doing any data transformation per se. What you are inserting is what you are getting, so there's no transformation. So generally that is 99.9% data coming through, unless somebody has put in a special character which is breaking something. But since the data team controls the SDK as well, and all the pieces of it, that rarely has happened for us.
Going from V1 to V2,
Yeah.
right? I mean, obviously, you would have built in resiliency, and you would have experienced some failures, right, as you moved along from V1 to V2. Um, uh, what was the, usually a design response time in terms of, when you identified an issue versus fixing it and redesigning it, and then making changes while keeping the whole thing alive, right?
Yeah,
So
so
I understand it's a painful exercise, but
yeah, so obviously, but that's the whole point also. Like, okay, then you get to talk about it because you have to go through the pain. For us, that was also very important that okay, our data pipeline actually cannot go down. We treat it as like ultra most important live service in the whole company. This cannot go down. If it goes down, you will suddenly see 30% of the office like sitting idle on their tables. Like they cannot query anything. So very important. It was we realized that okay, we have to do slow migration from a V1 to V2. So obviously you don't want a full boolean switch suddenly that okay, now we are on this amazing new system which can scale. So slowly, one by one microservice at a time. If we are changing something on the SDK side, then you do a very slow rollout across all microservices. Make sure all your sanity is fine. And actually, for that, only your data team is not, or data platform team is not enough. You need the data scientists as well, or the product managers themselves. We have just upgraded the system and wait for those 2 weeks to 4 weeks to kind of see if the data is all fine and there's no deviations which is breaking their alertings reports and whatnot, all the BI stuff. So that for different pieces that has to be done. Some pieces like okay, if you're changing something inside one of the pieces in the pipeline, but that is completely in your control, you still do a AB kind of stuff. You pass some traffic here and divert some of it, but if you're 100% sure and it's a standard release or standard upgrade, then you take those calls judiciously accordingly. Time frame, like okay, from V1 to V2? I think the design to this like okay, would have taken like a couple of months maybe. Like development aside, development is whatever it takes, and then after that, like okay, take a couple of months to make sure that okay, it's a smooth migration without any data losses and all that stuff, and we are never breaking the day-to-day flow of like, okay, oh, today you cannot do anything because our pipeline is broken. So, couple of months.
We can take one more question. Yeah, there's one there.
Hey, this is Anand.
Yeah.
You talked about going with the approach of using a thick client which uses a local storage before ingesting, right?
Yeah.
Maybe it is good for an optimization, but what about a possibility of losing a data, right? Because of like crashes, it could be, especially in case of your microservices where they're ingesting, right? How do you guys have those scenarios where possibly because of some crashes like instance failures you lose data and still you go with these approaches, you're okay with losing this data?
So good point. What we actually in the V1 itself, even the thick client was not inside the microservice itself. It was a separate microservice running where the microservices were running. Microservices had SDK inside, which are just writing on a local file storage. So that in the beginning itself, that's a call we ended up taking. Microservice itself should not go down due to a bad like data pipelines component. So they are just writing to a local file system, not even over network and nothing of that sort, just a local file system, so that that part is guaranteed. The max it can happen is your collector or your this client is broken and whatnot, and this folder or this particular disk is getting piled up. That's the worst which can happen, and you can fix that, or you can have different other like archival policies to cover for that. So that's how we ended up doing. The thick client was thick because it was actually reading those files and doing all that stuff and directly actually uploading to Redshift and S3. So kind of calling those over network data transfers as well. So you end up using resources of the instance, and that's why it was little slower, much slower than what we have now.
Okay. I know many of you have more questions. We will have a joint Q&A after lunch where Kumar will be back to answer more questions and more thoughts that you have. And you can also catch him outside. Thank you. A huge round of applause for this lovely talk. Okay, so while the next